So what do we got today?
Logistic functions.
Okay. Hold on, let me turn to that section. It's pretty unusual, actually. I don't get too many people that do logistics functions.
Yeah.
Okay. What kind of specific problems do you have?
In my book, it's number 7. It's compute the exact value of the function for the given x value without using a calculator.
Okay.
And it says f of x equals 3 times 5 to the x, or x equals 0.
I'm sorry, I didn't hear that function again. F of x equals what?
3 times 5 to the x, and x equals 0.
So, in other words, they want you to evaluate f of 0?
Yeah.
All right. What is f of 0 equal to?
Is it 3?
Yeah. In other words, any number to the 0th power is 1.
Yeah.
So this is 3 times 1. Okay? What else?
F of x equals 6 times 3 to the x if x equals -2.
Negative what?
-2.
So we want to do -2 this time. What is that equal to?
That is equal to, I don't know what 6 or 3 to the -2 is.
What's 3 to the -2 equal to?
I don't know.
Oh, it's 1 over 3 squared. In other words, whenever you have a negative exponent, it does not mean negative numbers. It just means the reciprocal.
Yeah.
So 3 to the -2 means 1 over 3 squared, which is 1/9 times 6 is 6/9, simplifies to 2/3.
Yeah.
Okay. What else?
F of x equals -2 times 3 to the x for x equals equals 1/3.
Okay, so here we're going to do what? -2 times 3 to the 1/3. What does 3 to the 1/3 mean?
It's, I don't know.
It's the cube root of 3. In other words, when you have a fractional exponent, if it was 3 to the 1/2, that would be the square root of 3. 3 to the 1/3 is the cube root of 3. 3 to the 2/3 is the cube root of 3 squared. So that's the way fractional exponents work. So we've got -2 cube root of 3.
So
that's the way to show the answer. That's the best answer.
All right.
Unless they told you to convert it to a decimal and round off to so many places. But there's no answer more accurate than this right here.
Yeah.
Okay.
That makes sense.
Yeah, any irrational number is better shown as a radical than it is a decimal. A decimal always rounds off an irrational number.
Yeah.
Well, so far we haven't really done much with logistics. We've done just exponential functions, which is part of that chapter for sure.
And the next one is slightly harder.
Okay.
I think it's 8 times 4 to the x, and x equals -3/2.
Okay, so first of all, what does that mean?
Oh, would it be 4 to the negative, or square root of 4 to the -3?
Well, first of all, let's convert the negative exponent to a positive exponent. What is 4 to the -3/2 equal to?
4, would it be 4 to the 5th?
No, it's 1. It's the reciprocal. Remember, negative exponents are reciprocal. So it means this. What is 4 to the 3/2 equal to?
It's equal to...
What's the square root of 4?
2.
And what's 2 cubed?
8. So it's 1/8.
Exactly. So that is 1/8. So it's 8 times 1/8, or 1. Just remember, try to remember that negative exponents do not mean negative numbers. They just immediately convert it to a positive exponent by putting 1 over that. Okay, what else?
Now, in your book, in mine it's number 13, but it says determine a formula for the exponential function whose graph is shown in the figure below, and it passes through 0, 3, and 2, 6.
Okay, 0, 3. So it passes through that. And it also passes through 2, 6. No, it's a little high for it. Let's make it twice as high as 3. And this is supposed to be some exponential function?
Yeah, we're supposed to find the exponential function.
Okay. Well, our standard equation is y equals a times b to the x, right?
Yeah.
Okay. Well, when when x is 0, we have 3. Well, no matter what b is, b to the 0 has to be 1.
Yeah.
So that means a has to be 3. You with me?
Yeah.
Okay, so y equals 3b to the x. Now we can solve for b by plugging in that point. So the y coordinate is 6. The x coordinate is 2. So I have b squared equals 2. So b equals square root of 2. So the equation that they are looking for is this. Now, let's just check this equation to make sure these 2 points work. When x is 0, this becomes 1. 3 times 1 is 3. So that point works. When x is 2, y should be 6. Well, the square root of 2 squared is 2. 2 times 3 is 6.
Yeah.
So this equation works. Okay. Oh, I'm looking at that problem right now, and mine is also 13. And 14 is this. Is that your 14 also?
Yeah.
Okay. So, let's go through the process again. Let's start with the standard format. Which point can I use to solve for A?
The first point, 0, 2.
Okay. So I've got y, which is 2, equals A times b to the 0th. Well, b to the 0th is automatically 1, no matter what b is. Therefore, A is 2. So now we have y equals 2b to the x. And now we'll use this point to solve for b. So what should I make y?
Y should be 2 over e.
And that's equal to 2b to the 1 power.
Yeah.
So what is b equal to?
Well, so would you would divide by 2?
Right.
So b equals 1 over e.
Which means that f of x, or g of x in this case, is equal to 2 times 1 over e to the x power.
Yeah.
And that's the way you want to do all of these. Now, hold on a moment. Yeah. Whenever your base of the exponential is a number less than 1, then you have decay going on. You don't have exponential growth, you have exponential decay, such as radioactive plutonium, as opposed to bacteria in a petri dish, which grows exponentially.
Yeah.
Radioactive material decays exponentially.
Yeah.
Which means the number here is always less than 1. That's the difference between decay and growth. Okay, which one you want to do next?
It's 45 in my book, and it's f of x equals 3 times 2 to the x.
Same. I've got that in my book also.
Yeah.
So we're supposed to graph it, analyze it for domain, range, continuity, intercepts, increasing or decreasing, symmetry, boundedness, extreme asymptotes, and behavior in concavity. All right. First of all, let's graph it. All exponentials go through, well, the way to graph this is to start with the first point by letting x equal 0. What is this function when x is 0?
3.
Okay. And all exponential functions kind of look like that, where this is asymptotic to the x-axis. In other words, if I go to negative infinity, f of x would approach 0.
Yeah.
All right, what's the domain of this function? What can x be?
Would it be 0 or negative infinity to infinity?
Yeah, all reals. It's a member of all reals is the domain. About the range.
That would be 0 to infinity.
And you're using interval notation?
Yeah.
Okay. Continuity. Is this continuous everywhere?
Yeah.
Okay. Intercepts. Do we have any x-intercepts?
Yeah, at 0, 3.
No, we don't. That is a y-intercept.
Oh, yeah, yeah. That would be like 0.
Is this increasing or decreasing?
Increasing.
Does it have any symmetry?
No.
Good. Is it bounded?
No.
Well, it's bounded on the bottom by y equals 0.
Yeah.
In other words, y equals 0 is a lower bound. Are there any extrema?
I don't know. I don't think so.
No, there aren't. No. In other words, an extrema has to be something like that. That's a local extrema, that's a local extrema. Well, in this case, there is no point on this curve where the surrounding points are both higher or both lower. And that's what extrema means.
Yeah.
Asymptotes.
None.
There's a horizontal asymptote. Y equals 0.
Uh-oh.
Notice that the definition of horizontal asymptote is what does the function approach as x goes to negative or positive infinity? Well, as x goes to negative infinity, f of x approaches 0. That's the definition of asymptote. End behavior. What happens as x goes to negative infinity?
It gets closer and closer to 0.
Okay, so that's yeah, that's the end behavior. As x goes to negative infinity, y goes to 0.
Yeah.
What happens as x goes to positive infinity?
It gets closer and closer to infinity.
Yeah, y goes to infinity.
Yeah.
What's the concavity? It's concave up. It's concave up. This is concave up. This is concave down.
That's up.
This is up. In other words, this is up. This is down. If I had a function such as the following, there is a point that you'll learn in calculus called an inflection point. The inflection point is the point that separates concave up from concave down. Notice that to the left side of this is all concave up. To the right side of it, it's all concave down. Concavity is a key mathematical point to understand.
Yeah.
Mainly with calculus, but All right, so looks like there's 4 or 5, I got 6 functions in my book that they want all of these things.
How about we just do 47 too?
47, okay.
Yeah.
Is that your 47?
Yeah.
Okay, let's graph it. What point does it go through on the when x is 0?
It goes to 4.
Yeah, 0, comma 4. And what does it look like? It looks just like every other exponential function. It's hard to tell exponential functions apart. They all have the same shape. That's y equal 2 to the x. That's y equals 17 to the x. By looking at it, I can't really tell the difference because they both go through the same point, 0, comma 1 and 0, comma 1. That's why they look so similar.
Yeah.
They're different, for sure. In other words, when x is 1, y is 2. Over here, when x is 1, y is 17. So this is a little steeper. But if I just showed you the curve without any grid, you'd be hard-pressed to tell whether that was 17 to the x or 2 to the x. So all exponential functions tend to look alike. Now, if you have a multiplier in front, like we do on this, like we have a 4, then it doesn't go through 0, comma 1, it goes through 0, comma 4. What's the domain of this function?
Negative infinity to infinity.
Okay, what's the range?
0 to infinity.
X-intercepts?
None.
Y-intercepts?
0, comma 4.
Increasing or decreasing?
Increasing.
Bounded?
Yes.
On which end and by what line?
Y equals 0.
Okay, any extrema?
No.
Any horizontal asymptote?
Yeah, y equals 0.
Okay. What's the next one you want to look at?
I think I only had a couple more.
Well, the next few are significantly different. We should look at least at 48, 49, or 50.
Okay. Let's look at 49.
Okay. So the function is 5 over. Now this is a logistic function. All right. What is the domain of x? Well, hold on. They want us to graph it, first of all. What point does it go through when x is equal to 0?
5? No.
5 over 5, which is 1. So when x is 0, y is 1.
Yeah.
Okay. Now, logistic functions typically, hold on. Logistic functions tend to look like this. They start out looking like exponential functions, and then they flatten off. like that.
Oh, sorry. Someone just called my mom on Skype, so I'm gonna
Okay. What do you need to
tell them that I'm not my mom.
So what do you need to do? Anything?
I'm just not looking at your screen right now.
Okay. Go ahead and take care of whatever you have to do, and then let me know when you're ready.
All right.
Okay.
Go ahead.
Logistic functions, as I said, they start out looking like exponential functions, and then they level off. And they kind of level off to a horizontal asymptote that they don't go above. This is a logistic function. The format of a logistic function is C, some number, over 1 plus A times B to the X. That's a logistic function. Well, that's what we're looking at. C is 5, A is 4, B is E, and it's to the minus 2x instead of to the x. So, let's see. As x goes to infinity, what would this y value approach?
5?
Yeah, good. In other words, that number right there is 5. And the reason is that 5 over 1 plus 4 times, well, that's the same as 1 over e to the 2x. Well, as x gets super big, this denominator gets big, this whole thing goes to 0, and you end up with 5 over 1. So the horizontal asymptote here is 5, y equals 5, and y equals 0. We actually have two asymptotes. And logistic functions tend to represent more of a real world. In other words, people say, well, bacteria grows exponentially, but it really grows logistically. Because no matter what the size of the petri dish, eventually the bacteria fills up the dish and it can't get any bigger. So it tends to level off. Same with population growth. Population growth, whether it's rabbits or human beings, starts out exponential. In other words, as long as there's plenty of resources around, populations will grow exponentially. But because all populations are eventually limited by their resources, they tend to have an upper limit as to how big they can get. And so they tend to follow a logistic function as opposed to an exponential function, as a lot of things do. There's not too many things that actually grow exponentially forever. I mean, if you think about that, it's going to grow and hit infinity pretty quick. So if anything actually grew exponentially forever, it would overwhelm the earth. Thank goodness that bacteria don't grow exponentially, but they only grow logistically. Same thing with populations. Okay, so our domain is what?
Negative infinity to infinity.
Our range is what?
0 to 5?
Yeah. Our x-intercepts. Y-intercepts.
At 0, 1.
Increasing or decreasing?
Increasing.
Always increasing. Now, not all functions are always one thing or another. This particular function is always increasing, even though very, very slightly at the end. But the fact is, it's always increasing. If I had a function like this, Well, it's increasing from there to there, and then it's decreasing from there to there, and then it's increasing again from there for the rest of the way. So
Yeah.
not all functions are always one way or the other. They switch around. Is this bounded?
Yes.
By?
Y equals 0 and y equals 5.
Good. Any extrema?
No.
Right. You might tend to think that 5 would be an extrema, but the function is actually never equal to 5. You can't find an x that makes it equal to 5. So, therefore, if you can't name the extrema, then it doesn't exist. In other words, if I've got a function like this, well, I can name that extrema right there. I can figure out where that maximum is.
Yeah.
So that would be an extrema, and then I have a local minimum here, and that's an extrema. But if I have a function like this, there's no extreme on that. Where is it? It's infinity is where it is. In other words, that keeps going up as x goes to infinity. But that means I can't name it. In other words, you can't name it with infinity. It's got to be something you can put a number on to actually be an extrema. And the horizontal asymptotes.
0 and 5.
Y equals 0, y equals 5.
Y equals 5, yeah.
Yeah, good. That was a logistic function. What next would you like to do?
My teacher recommended doing 55.
Okay.
And it's the using 20th century U.S. Census data, the population of...
That's my 54. Okay, so let's do that one. So the population as a function of time, is this your problem here?
Yeah.
Notice?
Oh, it's slightly different. It's slightly different.
Are the numbers slightly different?
Yeah, mine are 12.79 over 1 plus 2.402 e to the negative 0.0309. 309.
X?
Yeah.
T, actually.
Yeah.
In other words, the variable has to be t. That's what this means. We have a function of t. Okay. And P is the population in millions. And T is the number of years, in my book, since 1800. Is that the same as yours?
Since 1900 in mine.
Okay. T is the number of years since 1900. Okay. What is the population in 1850? Yours probably says 1950.
It asks when was the population of Ohio 10 million.
Okay. So when is P of T equal to 10? Because that's in millions. So I'm going to substitute 10 for that and solve this equation.
Yeah.
Notice that this equation only has one variable in it. E is a number, it's not a variable.
Yeah.
So all I have to do is solve that equation. And it will tell me when the population became 10 million. So let's talk about solving this equation. It's the first step.
Don't you divide by 12 point?
Well, not yet. Not yet. Let's get rid of a denominator. Equations are always hard to solve when you have denominators. Almost always the first step is to get rid of the denominator.
Yeah.
Well, I can multiply both sides by that whole thing. So that gives me 10 plus 10 times, well, 2.402 e to the minus 0.0309t. That becomes the left side, and the right side becomes 12.79. With me?
Yeah.
I can actually multiply this 10 here by the 2.4, making it 24. Still with me?
Yeah.
Now let's solve this. How are we going to solve this?
Would you...
We want to end up with t equals something. Now, this is not an algebraic equation. This is an exponential equation, which means most likely we're going to need to use logs to solve it. Almost always you have to use logs. But the goal is to first isolate that.
Yeah.
So how do I isolate that?
So first I would subtract 10.
Okay. Now what?
Now you would divide by 24.
0.02, yeah.
0.02. And
now what? Let's get a number on this. What is that number equal to? You have your calculator handy?
Yeah, I do.
It's about
it is
1/12. It's about 0.1 maybe.
2.1 divided by 24.02. It is 0.1161.
Okay. So now this is our equation. Now this is the key step. What do you have to do to solve for t here?
Wait, what is E?
E is just a number. It's 2.71 and change. It's like pi. It goes on forever.
Yeah.
Okay. But here, okay, let me go through this solution for you. Whenever you have your variable in the exponent, there's no algebraic way to solve for it. But there is a logarithmic way to solve for it. Algebra tells me that I can do anything to the left side of the equation as long as I do it to the right side. Well, the thing I want to do is take the natural log of both sides.
Yeah.
Okay? Now, once I've taken the natural log of the left, well, because natural log is base e, and because log base b of b to an exponent is equal to that exponent, the whole left side simplifies to the exponent. The whole right side is a number. That is just a number. So now how do I solve for t?
You take the, or you divide by 0.0309.
Negative
0.0309.
Okay. Now, when you take logarithms of numbers between 0 and 1, the answer is negative. Always. If you take the natural log or any kind of log of a number greater than 1, you get a positive answer. You can't take the natural log of negative numbers. It's against the rules. So any log of a number between 0 and 1 is negative. So this is good. In other words, the numerator is going to be negative and the denominator is negative, meaning that our time is going to be a positive number, which it better be. We don't want to come up with any times that are negative numbers. So what is the natural log of 0.1161?
It's going to be negative something.
Go ahead and get it. On your calculator, what kind of calculator do you have, Lucas?
The TI-83.
Okay, you got two keys on it. You got a log key and you got a natural log key.
Yeah.
Find the LN key.
Hold on. I think I have a better calculator. Well, I can't find my calculator.
Okay. Well, you're going to need a calculator that can do logs.
Yeah.
You're not going to be able to answer any of these problems without it on this chapter.
Yeah.
This whole chapter is exponential, logistic, and logarithmic functions. All of them require you to be able to do logs.
Yeah.
So if I put this in Wolfram alpha to come up with an answer, what is it? It's the log of 0.1161, natural log of 0.1161 divided by negative 0.0309. Negative 0.0309. Okay. That's what I put in. And it gives me an answer of, wow, 69.68. So T is equal to 69.68. So their question was what? When will the population be 10 million?
Yeah.
69 years after 1900, which is not in 69, because it won't quite be 10 million. So, no, 1969 will be the year where it hits 10 million. About 2/3 of the way through. In other words, in 2/3 of the way through the 69th year, the population will hit 10 million.
Yeah.
So I'm not sure. What was the question? What year will the population hit 10 million?
It was the number of years, yeah. Yeah, it was.
Well, it matters exactly how they worded it, because it would be 1970 if they worded it like that. If they said, what year will the population hit 10 million? Well, in 1969, it doesn't hit 10 million. No, actually it does. 2/3 of the way through it, it does. 1969 would be the answer.
Yeah.
Okay.
And then the last one was, it's 57. It's about bacteria growth.
Okay, that's number 55 on mine. Why don't you read me what yours says, though? What's the equation?
B equals 100 E to the 0.693c.
Same as my book. What was the initial number of bacteria present?
So at 0?
Uh-huh.
So would it be 100?
Yep. How many bacteria are present after 6 hours? Right?
Yeah.
Well, that's just, you need to solve that on your calculator. So that's, in other words, that's relatively easy. You don't need logs for that. Because all you need is to take the number e to the power of whatever that number is.
Yeah.
Which would be about 4. So it's 100 times e to the 4th power, basically, which is like that's like 60. So it would be like 6,000. So it goes from 100 bacteria to 6,000 bacteria in 6 hours.
Yeah.
That's why infections are so bad. What else?
That was the last one that I had, so.
Okay. Well, we don't need to go any further than that. If you don't have any other questions, we can end the session now if you like.
That'd be fine. I think I have a...
Yeah, when I end it early, I only charge you for 3/4 of an hour.
Yeah.
So, and that's fine with me. I don't have any problem with that.
All right.
Okay? All right, Lucas, I will talk to you next Wednesday.
All right.
Bye-bye.